All right, so I'm going to go over some of the properties of ionic compounds. We've talked about ions. I'm going to go over some properties of ionic compounds and then the naming of ionic compounds, which is pretty simple, I promise. So ionic compounds tend to have very strong bonds holding them together. And because of that, ionic compounds have pretty high melting points and boiling points. Some other properties, they are solids, and we say crystalline solids at room temperature because the crystalline means that they form crystals. And ionic compounds, each ionic compound actually forms a very specific shape of a crystal. So, for example, this is sodium chloride. I'm going to erase this really quickly. And I can show you when you're in here, but I have some samples of sodium chloride crystals. Let me get rid of that because that has nothing to do with this. Sodium chloride is composed of the sodium ion, right? That's positive, and the chloride ion, which is negative. And then of course, the positive ions are attracted to the negative ions. And so they form this, the positive ion wants to be completely surrounded by negative ions, right? And then the negative ion wants to be completely surrounded by positive ions. And certainly in terms of like the chloride ion, which is negative, does not want to be next to another negative ion because those like charges repel each other. By the way, I don't care about this. Don't worry about that. So this is kind of a picture of if green is representing this chloride ion, you can see that each of the green atoms here is completely surrounded by a white. And because it does that, it forces this into in a very specific shape. So we look at one of the chloride ions and we have, right, the sodium ions surrounding it. If we look at a sodium ion, we have chloride ions surrounding it on all of the sides. So this is why ions actually are found in very specific crystal structures. We don't find this same very specific crystal structure with covalently bonded molecules, which we'll talk about right after this chapter. So sodium chloride, as it turns out, makes a perfect cube of a crystal. They're actually beautiful. They look like little square diamonds. And again, it's because of that, those opposite charged ions do not want to be next to each other. Okay? One thing, and we can actually do a lab on this. This would actually be really fun. When snow days is over and we have some time, we got to get some labs done because there's some really cool ones that we can do with this chapter or with this unit. So these, the cool thing about ionic compounds is they conduct electricity when they're melted or dissolved in water. And so we can do some testing of that actually. The other type of bonding that I want to kind of go through really quickly is metal bonding. So metals always form positive ions, and yet we can have a sample of metal, and metals have unique properties that are different than nonmetals. And we can have a sample of metals in which, you can have a large sample of copper or a large sample of iron, for example. So if they form positive ions, why do they stay together and why don't they repel each other? As it turns out, metals are surrounded by, metal atoms have electrons. They either have one or two, typically, valence electrons, and they don't hold on to them very tightly. Remember, they want to give up their outer valence electrons in order to achieve that stable octet. So they either have to pick up, a whole bunch more electrons to achieve that, or they're going to give up their one or two. So they give up one or two. But what happens when you have a sample of metal atoms together is, we talk about this concept of the sea of electrons model. They don't hold on very tightly to these valence electrons, and so they kind of share them with all the other atoms of metals that are in this sample. So we say that the positive ions of metals are kind of surrounded by this sea of electrons when you have a sample of metals. Because of that, we have specific properties in metals. For example, metals are good conductors of electrical current because electrons can flow freely through metals. And that has to do with the fact that, yeah, these electrons are kind of moving and being shared around all of these positive ions of metals. By the way, I want you to be writing this stuff down, so please take notes with this. Metals also are very ductile, that is, they can be drawn into wires. And this is how wires formed. It's pushed through a mold that makes it that very specific shape. If we tried to do this with ionic compounds like imagine table salt, it would just shatter, right? So this is unique to metals. Metals are also malleable, and then they can be hammered and shaped. And again, if we tried that with an ionic crystal, obviously it would just shatter. But with metals, we can actually shape them into things by pounding on them. Oh, I don't care about this. Just kidding. I'm going to skip through the crystal structure part. The other thing I wanted to talk about is what an alloy is. So alloys are made of metals. At least one of the elements is a metal and one is a non-metal. And so it's a mixture. It's actually, they're not chemically bonded together, but it's a mixture of two or more of those atoms, at least one of them being a metal. And the reason we have alloys is it somehow makes them superior to whatever that metal is alone. So it either makes the metal stronger or makes it last longer. Maybe it doesn't rust as easily and so on. So there's lots of reasons. So bronze, for example, is a mixture of copper and tin. Sterling silver, which is popular in jewelry, is silver and copper. Silver tarnishes really easy. And interestingly enough, so does copper. But when we mix them together, sterling silver doesn't tarnish as easily. It's a little bit superior to either of those by themselves. Let me see. And steel, that's the other one I wanted to mention. So steel, we don't need to know this one. Oh yeah, we probably do at some point, just kidding. Steel actually is iron and then carbon, which is a non-metal. And it just, again, it makes that iron stronger and it keeps it from rusting as quickly and oxidizing as quickly. So there's two different classifications of alloys. We either say it's a substitutional alloy or it's an interstitial alloy. If it's a substitutional alloy, the different atoms that make this alloy mixture are about the same size and they just sort of, kind of arrange with each other. If it's an interstitial alloy, one atom is much smaller than the other. The smaller atom just sort of fills in these little spaces in between the larger atoms, and that's what we would call an interstitial alloy. Those are just the two classifications of alloys. But again, lots of reasons why we have alloys. Okay, and then the next, kind of the last part for this unit, and then we'll be gearing up for a test on this, honestly, after we do a lab or two. But monoatomic ions, that's, so ions consisting of one type of atom, and this is kind of the first atoms that we did. So polyatomic are the ions that exist of more than one element bonded together. So monoatomic ions consist of one type of ion. In naming, so we're just going to go through the naming, super easy with ions. So first of all, we always put the positive ion first. That's really important. So naming cations, and I always remember cats are positive, right? So cations are like, cats. They're always the positive ion. Cats go first. Anions, onions are negative, so anions are negative. So when we look at naming ions, we always put that positive ion first. So in this case, copper. And remember, whenever you have a metal, metals are always positive too. Over 80% of the elements on the periodic table are metals. when you learned about the periodic table. Hopefully you did. So anyway, so positive ion goes first. So the copper ion goes first. The negative ion goes second. Actually, I'm going to do a simpler one here first. So one that we look at might be, so if I have this compound, Mg, which is a +2, chlorine is a -1, so MgCl2, what would the name of this be? You can consult the ion sheet that I gave you, and it's literally the first ion is just the name of the element. So magnesium. The second ion, so this is the element chlorine, but as an ion, it's called chloride. So the name of this compound is literally just magnesium chloride. The positive ions, we just call the magnesium as an ion, is just called the magnesium ion. Chlorine, the anion or the negative ion, it's not called the chlorine ion, we call it the chloride ion. So this is magnesium chloride. Super simple. For polyatomic ions, we just use the, again, the names that are on that ion sheet. One other thing that we need to understand, and I know I've mentioned these Roman numerals. So the Roman numerals tell me in the name, so if I have the iron 2 ion, that means it's iron with a 2+. Iron 3 ion becomes iron with a 3+. When I look at something like this, I kind of need to work backwards and say, well, how do I know that if this is iron 2 or iron 3? At first you might say, oh, there's a 2, so I think it's iron 3. But remember, we use the crossover method, so this has to be iron with a 3+, and oxygen has a 2- if you look on your ion sheet. So this is iron 3. So the way I would write this formula, so iron 3 oxide. Because there's more than one form of ion or iron, I need to show that I know that it is in fact iron 3 oxide. So someone can look at this if they didn't see this. You know, if you weren't given this part, if you saw this, you would know it's iron with a 3+. This particular one, again, I know it's iron. I have to look up this ion. Well, I don't have to. I can tell by the formula if I work backwards. This is going to be iron with a 2+. Since there's no subscript here, this must just be a -1. So this would actually be iron 2 hydrogen carbonate. And again, I always feel like this is an ion that throws people. This is all one ion. If you look on your sheet, it's called, it's just called the hydrogen carbonate ion. People try to break off the hydrogen. Nope, this is all one. So, all right, so I'll have a sheet for you to work through on this. Check with the librarian. And then take the quiz for today too. Thank you.